All right, so previously I talked about atmospheric composition and chemistry, climate and radiation, and now atmospheric evolution. And again, I have a fairly solar system perspective, and I'm particularly interested in the Earth and its neighbors. So what I'm going to talk about, the origin of atmospheric volatiles and the Earth's first billion years. A volatile, in this sense, is a substance that's liable to form a gas or vapor at the prevailing temperatures. So water, carbon, nitrogen, sulfur, that kind of thing. Then I want to talk about the effect of life on Earth's atmosphere, which is relevant for exo-Earths and finding life elsewhere in the galaxy. And then we heard from Ruth Murray Clay a bit about atmospheric escape. And I'm going to talk about that more in general. It can sculpt atmospheres, it can remove them, it can change them chemically. So for example, Venus's atmosphere is the result of escape, and yet it's really thick, but it's selective escape of hydrogen and probably some oxygen that got dragged along. Atmospheres and origin of the volatiles. I'm not going to talk about the solar nebula much and accretion, but start from the basics, the beginning of having an atmosphere. So volatiles mainly come from asteroid material, and that's verified by celestial dynamic models, and also looking at isotopes for, say, the Earth, where we have really good information. We can look at the D2H, which matches that of water in meteorites from the asteroid belt. We can look at N isotopes, which matches that also. And the dynamical models show that asteroid material is likely to have provided the majority of, say, the Earth's water, whereas comets would probably be no more than 10%. And these were acquired during terrestrial planet accretion, which can spread over as much as 10 to the 8 years. A caveat is that some primordial component might be retained inside a rocky planet from the stage of accretion where you have a magma ocean, and there's some evidence for that for the Earth. If we compare the Earth and its neighbors, then something reminiscent of Tolstoy's Happy and Unhappy Families happens, which is the volatiles are acquired in the same way, but volatile depletion on each planet is depleted in its own way. If we look at this graph, which basically is a bunch of elements, refractory ones, geochemical volatiles like carbon, zinc, and chlorine, and then atmophiles, so volatiles that like to sit in the atmosphere. And we can look at these abundances relative to solar composition from carbonaceous chondrites, which would be up here, and we can look at Mars, Venus, and Earth. And if we look at Venus, for example, we see that it's extremely depleted in water. If we look at Mars, it's depleted in all of these atmophiles. And otherwise, Venus somewhat tracks the Earth. So Mars, we can see, evidently lost air. Why was that? Probably the predominant reason was atmospheric escape, being a smaller body, but also there could be volatiles locked up as solids because it doesn't recycle them. But I talked last time whether Venus might have had an ocean for a while before going into a runaway greenhouse effect. We can get clues from noble gases. So for example, Venus has only a quarter of the argon-40, which comes from decay of potassium-40, found in the Earth's atmosphere. So bizarrely, although it has a thick atmosphere, it doesn't seem as degassed, perhaps, as the Earth is. And perhaps that's because it simply doesn't have the plate tectonic regime that the Earth does, which is continually churning stuff around and making the argon-40 come out. So if Venus did have an ocean, presumably perhaps it didn't last very long if it had a stage of plate tectonics or some other tectonic phase. Yes? Yeah. You mean relative to Venus? Yeah, well, Venus has a surfeit of certain noble gases, which has been hypothesized to be just a sizable comet that happened to hit stochastically relative to the Earth. It's like a 1 in... So Kevin Zonnelly, who's sitting next to you, calculated that there was a 1 in 4 chance or something of the appropriate comet coming in and boosting its noble gases. But for Mars, you know, this is a primordial isotope, and there's clearly a lot of atmospheric loss, and we can explain that from impact erosion or hydrodynamic escape. This is a diagram, a timeline, showing solar system formation after the oldest objects. So calcium aluminum inclusions, which are found in chondritic meteorites, which are dated at this time 4.568 billion years ago. So this timeline starts from then. And the Earth, the proto-Earth, would have formed during this timeline. So this would be 10 million years and then tens of millions of years. And during this time, it had its first atmosphere from when the impacts are coming in, vaporizing and degassing their volatiles around the proto-Earth. And then there's the moon-forming impact, which would have been followed by a similar kind of impact degassing. So this is, these are some plots. Kevin's responsible for these. And basically, it shows you impact degassing of accretion and having a steam atmosphere, which is of order 100 bar. And this means that you have a blanket which blocks out infrared, thermal infrared radiation. So you're in a runaway phase, so the surface melts. And then, as the impacts decline and as things cool off, you'll have a collapse. The steam will collapse to an ocean near the Earth radius. So after the moon-forming impact, this kind of thing happened, and here's a semi-quantitative graph. So here's time in years, and first of all, we have a steam atmosphere, which, let's see, then collapses at this point into oceans. Then you're still left with a lot of carbon dioxide in the atmosphere, and this will be removed by reacting with the crust. And what you're left with is maybe a phase that lasted as long as 10 to 8 years, where you've got a lot of carbon dioxide gradually being used up, reacting with the crust and a salty ocean. And then you've got, for the Earth's history, you've got this eon called the Hadean, 4.5 to 4 billion years ago, and we don't know much about the atmosphere then. The reason is that we don't have sedimentary rocks from this period, so we just don't have the geochemical clues as to what was going on. And therefore, it's open to models which can diverge quite a bit. After that time, people have looked at impacts on the moon, like Nectaris, Imbrium, Oriental, and this graph is really showing you a justification for this sort of idea that's been around for a number of years called the late heavy bombardment, which is when you date these craters on the moon, you find that the very large craters cluster around 3.9 billion years ago. A lot of people think this is an artifact of sampling one particularly large crater, Imbrium, and getting the debris from that and this contaminating the age dates. But if you took this as being an estimate of the impact bombardment rate, and then you extrapolated back, you would have the moon accreting at 4.1 billion years ago. So that doesn't work very well. So therefore, people propose that there was some spike of bombardment at this time. A lot of work has been done recently on this by Bill Bottke, looking at, say, Vesta meteorites and doing dynamical models and suggesting that this is an extended perhaps an extended phase where there was some sort of late heavy bombardment. It's also true, as far as we can tell, or the age dating is not very good, that there are a bunch of large basins on Mars at this time. Going back in this phase, in the Hadean, if you're hit by a 500-kilometer size object, then that's enough to vaporize the entire ocean with its kinetic energy. So the Earth would have been periodically sterilized if objects like this hit, and smaller objects wouldn't vaporize the whole ocean, but just the upper ocean. So maybe 1 to 4 of these complete ocean objects hit and would have killed any incipient life. So life developed here, but could have been killed off, and the oldest evidence for life on Earth is about 4.1 billion years ago. It comes from carbon isotopes in what's interpreted as relict organic matter in zirconium silicate crystals, which are very hardy to erosion and tectonic processes. And it's been speculated that the impact bombardment on the early Earth may have, by killing off life, may have restarted it, and the only things that survived were thermophiles, heat-loving microbes. And this is a tree of life with us up here in the animals. Here's the bacteria, the archaea, and us eukaryotes, creatures with cells with nuclei in them. And if you trace it back, down near the root are thermophilic microbes, so that your great-great-great, insert lots of greats, grandmother was a thermophilic microbe, heat-loving microbe, this last universal common ancestor. And so it's been proposed that a big impact pruned the tree of life back, and it started again from a thermophile. But there are some geneticists who question this, because it turns out that the thermophile genes are by their nature very hardy, and even the bonds in the DNA, the RNA, will persist and not change as much. And so this might be an artifact of just the nucleotides in the RNA surviving and appearing to be older than everything else. I said that we could tell that volatiles came from asteroids, and one way of looking at that is the deuterium-hydrogen ratio. So here's the Earth, oceans, and here's carbonaceous chondrites, a histogram of their values, which fits nicely, but ordinary chondrites, which are more abundant, don't fit so well, and neither do some other things. And it's certainly different from a solar abundance. Jupiter family comets, so these are long period comets here, like Halley. But Jupiter family comets, ones from the Kuiper belt, that's what that means, have a spread of values. There are not too many have been measured yet, and one of them has a similar deuterium-hydrogen ratio to seawater, but its isotopes of nitrogen are different. And the Rosetta comet, mission comet, has a D2H which is different still. So we don't really know what the average is for Kuiper belt objects, given these values that have been measured or inferred, and are very different. But it appears that comets don't match the Earth's oceans, whereas asteroidal material does, at least carbonaceous chondrite material. What we don't know is what the Earth's atmosphere and climate was like during the Hadean, with some people suggesting it was hot, some people suggesting it was frozen, because there's a fainter sun, and so there's a lack here. And another big question is whether there is a reducing atmosphere on the very ancient Earth, conducive to the formation of organics, like on Titan. Oh, okay. That's true. So people, that doesn't match with the carbonaceous, but I think it's better with the ordinary chondrites. So people talk about a large component of the Earth coming from the ordinary chondrites, but you don't need much carbonaceous chondrite to supply the volatiles, because they've got, for example, in organic carbon, they've got 2 to 3.5 weight percent. So if you made the Earth of pure carbonaceous chondrite, you'd end up with too much carbon. You only need a tiny fraction, and only a tiny fraction of those for the water. even though so you have to basically mix together various components to match all the different isotopic systems. And it doesn't always work for everything.
I thought also was I'll look at the reference and tell you that it's just for properties, but I thought it was for all.
Is it? Okay.
The story that you told about volatile delivery is the one that I've always heard. But then recently I was talking to some chemistry scientists who asteroids a lot. And I said that actually, even in the dry ones, there's a much higher water content on the Earth.
Yes.
And recent models of moon-forming impacts actually show that it's difficult to get rid of that water. So they were saying that you don't need any additional volatile delivery later. The problem is actually getting rid of all of the volatile scarlet. So I'm wondering if you have an opinion about that.
I'm not arguing necessarily for some late veneer of volatiles. I'm just arguing in general that the data seems to support that they're delivered by asteroidal material.
Which could just be the planetesimals that form the Earth in the first place.
Yes. Let's see. So another question is whether it had a reducing atmosphere and produced a lot of organics from the photochemistry that I talked about earlier, like on Titan. And also, if you had hydrogen, that would produce a lot of greenhouse warming. And perhaps one access to this in the future would be interesting to look at young Earth-sized planets and see what kind of atmospheres they have. So a milliuri atmosphere, for anybody who doesn't know, is a kind of atmosphere named after Stanley Miller, who did this famous experiment where he put reducing gases in a flask and sparks to simulate lightning and made amino acids, the building blocks of proteins, in the process back in the 1950s. And so if you have a reducing atmosphere, then when the molecules break up, the free radicals you produce can produce things like amino acids or even the nucleic acids of genetic material. And this fell out of favor because people realized that when we look at volcanoes today, the dominant gases coming out are things like water and CO2. They're not the reduced form of hydrogen, which would be hydrogen instead of H2O, or the reduced form of carbon, which would be CO or methane. In fact, if you go to a high-temperature volcano, you won't find any methane coming out of the main crater. It's too hot. The thermodynamics don't favor it. It comes out as CO2. So basically, if you have an oxidized mantle, it produces oxidized gases. And if you have a reduced mantle, say with iron in it, then it will produce reducing gases from the chemistry. So during core formation, before the iron is dropped down into the core, you could have this situation, but this lasts only for tens of millions of years. And so after core formation, the subsequent atmospheres should have been oxidized based on mantle geochemistry. But there's still a lot of debate about whether there were bits and pieces in here that were not fully oxidized and whether they got mixed up at certain times, and whether there was a more gradual oxidation of the mantle rather than some kind of binary step like this. Yes?
What sets the time scale of settling time?
It's a settling time if you do a model. Yeah. I think Dave Stevenson was the first one to look at this problem back in the maybe late 70s, early 80s.
But you could still have a reduced atmosphere if you have residual, reduced gases, and they're slowly getting oxidized by this kind of stuff, right?
I'm not sure what you mean.
What if you had a bunch of hydrogen left over from formation and it just was taking over?
Oh, you mean if it took a long time to escape or something?
Yeah.
Well, it generally doesn't take a long time to escape. That would be the answer.
But, there are people who talk about early Earth having a lot of hydrogen on it.
You would have to throttle the escape somehow or another. So if you calculated the escapes using standard theory, it would escape rapidly. But if you had some very atmosphere that was dramatically cooled at the top of the atmosphere somehow, that might throttle the thermal escape. So you would have to play with that kind of model. It's the kind of thing that heavens only, would like to play with. Yes? Let me see. There was a paper published about this within the last couple of years, but I think the data was only in the Archean, where we have good rocks. And before that, it's theory. But at least in the Archean, which is from 4 billion years ago to 2.5 billion years ago, there's evidence for a magnetic field, except it may not have been the same strength. I think the paper argued that it may have been weaker, but for reasons that were unclear.
I guess for purposes of things like atmospheric escape, that first sort of 100 million years is really critical of whether or not you form a magnetic field instantaneously as soon as the differentiation happens, or it takes 100 million years.
Yeah. Right. Well, to the extent that a magnetic field protects you, and I'm not sure that it does, from the extreme ultraviolet of the sun driving a hot thermosphere and driving a hot exobase and causing escape. Well, I'm going to move on. I'm going to move on at this point. So basically, Earth's volcanoes are letting off steam and some other minor gases. Well, CO2 is quite significant, but the reducing gases are minor. Nitrogen also comes out of volcanoes, difficult to measure since we live in a nitrogen atmosphere, but that nitrogen has an isotopic signature of being partly recycled from organic matter that contains nitrogen and goes down in the tectonic regime. Hydrothermal lower temperature emissions, or even the lower temperature emissions on the flanks of volcanoes that are subaerial, at lower temperature tends to favor the more thermodynamically, the more reducing gases. So those are a bit more hydrogen rich. So if you did have an oxidizing atmosphere on the early Earth, there's always going to be places where it will be locally reducing, such as here, and so some people favor such environments for the origin of life. After the Hadean, for most of the rest of...
Reduction is so good for early life. Is it that oxygen just destroy everything that's...
You have to, we're made of organic carbon, and if you put an apple out, it will oxidize and turn brown on its surface, right? and that oxidation process destroys the organic molecules and turns them into carbon dioxide again. Yeah. So the kind of prebiotic chemistry needed for the origin of life doesn't work in an oxidizing atmosphere. Also, simple metabolism is a lot easier in a reducing environment. You can actually it's thermodynamically favorable to make bigger molecules in reducing conditions. That's not the case in oxidizing conditions, so to speak. There's a free lunch in a reducing environment that you're paid to eat, is whatever Schock says. So on geological timescales then, carbon and water get recycled. So water goes down in the slab and it comes up in volcanic arcs or at hotspots like Hawaii, or at island arcs like Japan, or this would be the Cascades in the Pacific Northwest, for example. And this is important to maintaining the Earth's habitability, as I mentioned last time with the carbonate silicate cycle. But of course, how this works on another planet, a rocky exoplanet, depends on tectonics and whether you could get different styles rather than the style we have here. But at least here, it's probably been operating something like this, maybe not the modern style of plate tectonics since the Hadean. What we don't know are even the volcanic gas composition on our neighboring planets. So what was it like on early Mars when volcanoes like Olympus Mons were erupting, the largest volcano in the solar system? Was that also similar to the composition of gases from the Earth's volcanoes or not? And there's some evidence from Martian meteorites which suggests that it may have had a more reducing mantle, in which case a lot more hydrogen might have come out of Martian volcanoes, and that could have made Mars quite a different place than the early Earth, perhaps more, in some ways, favorable for the origin of life and maybe help maintain its climate system. And of course, what's the zoo of possible exoplanet volcanic gas compositions and the way that that might affect their atmospheres? Unknowns. Now I'm going to talk about the effect of life on atmospheric composition. The exoplanet relevance here is detecting life or not. We often think of oxygen as biotic because that's how it's produced from green plants and cyanobacteria and algae on the Earth. But at one time on the Earth, there wasn't green plants, algae, and cyanobacteria. So on the abiotic Earth, what would oxygen levels be? And the key to thinking about this is that it's actually the hydrogen escape that produces the abiotic oxygen. So if you have water vapor photolysis, and then you have reactions that make oxygen from the products, this oxygen can recombine back to the water vapor, but it can't if the hydrogen escapes. Then it's actually a net source of oxygen. And you can also make oxygen from CO, and this can make oxygen, but there's still hydrogen associated with that. So whether the oxygen is coming from water vapor photolysis or CO photolysis or wherever it's coming from, it's still the hydrogen escape that's ultimately the net source of oxidation. And so when you do calculations with photochemical models, you produce some abiotic oxygen, but it's so small that it gets mopped up by any reasonable assumption of the hydrogen that's outgassing from the solid Earth. Basically, there's a net reaction that reconstitutes the water. So the amount of oxygen you get on the prebiotic Earth is extremely small. Now, there are pathological cases that people have looked at in the literature where they're generating oxygen-rich atmospheres that might be relevant to exoplanets. And that remains to be seen, whether you could have such things or not. But what's critical is that some of those models neglect outgassing, or they make very modest assumptions about the outgassing to boost their abiotic oxygen levels. And so you need to look at the details of their model and be skeptical about that. And the oxygen, of course, can also get mopped up by reacting with any reducing surface material, particularly if water's around, to enable that, as you know from your rusty bicycle. Yes? Well, you can take the modern amounts of outgassing, and if you just take that, you'll still have very low levels of oxygen. But typically, people think there were higher rates of outgassing because there are more radioactive materials in the inside of the Earth, so it's hotter mantle, and so probably had more outgassing at that point. And there are thermal evolution models of that, which typically estimate, if you go back, I don't know, 3.5 billion years, the factor would be somewhere between 3 to 5 to maybe 10 times more outgassing. But it's not, the exact number's not known because models differ.
But if you want to get the modern rate, do you just try to measure it at individual sites and scale it up? Or is there a measurement you can take in the atmosphere from which you can infer the rate of outgassing?
You can do both, but people typically, I think most of the estimates in the literature are from measuring gases from various volcanoes and summing them all up. Yeah.
So there must be a lot of uncertainty in that.
There is a lot of uncertainty in that. And even on carbon dioxide, there's quite a spread of different.
There isn't another way to look at this. You can look at water that's in seawater dissolution and fraction. It gets soaked up, then react against the mineral buffer of your choice, and then you'll get H2 and water is proportionating at a rate of something like 1 to 100, and you can get an H2 lower hydrogen flux from that, because you know the lower rate of C4 production and the lower rate of C4 production. And that gives a number that's somewhat on the low side compared to popular numbers, but certainly.
And it's on the low side because that's just dealing with high temperature volcanism, whereas there's lots of low temperature stuff that thermodynamically favors the more reducing stuff. Eric?
I just wondered if I could get you to go into a little bit more detail about your concerns about outgassing. Because there were a couple papers, I'm guessing probably some of the ones you're referring to a few years ago, about buildup of abiotic O2 for planets around the mid to late amulets.
Mm-hmm.
And it suggests by people like Rodrigo Luger,
Mm-hmm.
also at Washington, it suggests you can build up a couple hundred bars of O2.
Mm-hmm.
And this would be really important for any future biomarker detections. So do you think that from that much O2, a couple hundred bars could be soaked up by reasonable outgassing and environment?
Probably not in that particular case, but it's still dependent upon the assumptions of how much water is there initially and how much oxygen gets dragged out with the hydrodynamic escape of the hydrogen and so on and so forth. And also, actually, you know, whether in those situations, if you have a steam atmosphere, then you get a runaway greenhouse effect, and you can have melt the surface, and that can go down to some considerable depth if you have perhaps, and then you maybe have an efficient sink for the oxygen. And I always draw the counter case. Do you know what the oxygen level is on Venus, which we know had a runaway greenhouse? And there's not almost none, it's undetectable. So where's all the oxygen gone on Venus then? Smarty pants. So, and I think probably most of that, well, some of it got dragged out by the hydrodynamic escape, but a lot of it probably just reacted with the subsurface, but we don't know that for sure. But it would seem it's got to go somewhere, and it's not there. It got lost somehow.
That was probably only, what, a few bars?
No, much more than that, because well, it depends how much ocean was there.
I don't think you realized it was a longer water ocean or a fraction of ocean.
Well, there's an Earth ocean sitting on the Earth, but there's also half an Earth ocean, upper estimate, swirling around the crust, and maybe 2 to 5 Earth oceans in the mantle. If all that's on the surface of Venus, there's maybe more than an Earth ocean. Yes?
I just wanted to add to that there's a recent paper by Laura Schaefer and Dr. Sassalon, which looks at what the oxygen uptake if you had this case. Because when you're talking about these early M stars, and these 100 bars of oxygen, that's only for like the human sequence, right? And so they did a model that incorporates an interior to then say you would actually only expect, you wouldn't expect in the atmosphere
They go into a magma ocean, right? Yeah. So if we have a little oxygen, how much hydrogen do we have? And this depends on the escape rate. But you can imagine there's a source, which is the volcanoes and metamorphism, and there's a sink, which is escape. And for something like diffusion and limited escape, which I'll come to a bit later, you would estimate only maybe 1% of hydrogen. But you can get more hydrogen if you can somehow throttle this escape. But that is something I mentioned earlier. For the other prebiotic gases, it's a simple principle. A kinetic balance between sources and sinks determines its abundance. And so for CO2, it might be quite a bit higher than today, 0.1 bar to a bar. For nitrogen, Venus, remember, has about 3% nitrogen in a 90-bar atmosphere. So it's like 3 bars of nitrogen, roughly. And so it may have been the case that the Earth had a lot more nitrogen, the early Earth, than it does today, 0.8 bar today, right? And maybe 3 bars on the early Earth. So again, you just can play this game, but you have to estimate what this weathering sink is from the seafloor and from reaction with the continents. This would also apply to rocky exoplanets. So what happened when microbial life appeared? What happened to the air? Several things. One is that microbes like to eat hydrogen. It's good to, whoops, how did that happen? Microbes like to eat hydrogen and turn it into methane, because methane is less edible. Hydrogen is really yummy. And they do that like this. If there's some CO2 around, that makes a greenhouse gas and can affect the climate. Non-oxygen producing photosynthesis, like this, for example, can use hydrogen to make organic matter, basically to reduce the carbon dioxide chemically. And that can also be turned into methane. So that would produce even more methane and extract even more hydrogen. And then microbes also extract nitrogen from the air, nitrogen fixation. So in your body, about half of the nitrogen comes from the industrial Haber-Bosch process of fixing nitrogen. And the rest comes from the traditional way, which is microbes fix the nitrogen, which went into the peas or whatever that you ate and into your body. But the origin of nitrogen-fixing microbes would have drawn down the nitrogen from the air and perhaps lowered it to values that were similar to present or even less than present, because the return path of nitrogen, called denitrification, uses oxidized intermediates, which exist today because there's plenty of oxygen around, but wouldn't have done on the early Earth. And in fact, estimates of nitrogen in the last few years, papers ranging from 2012 to 2016, suggest that nitrogen may have been lower, less than half a bar compared to today, 0.8 bar. And the nitrogen rose as oxygen rose. And that maybe on the early Earth, as I was speculating earlier, nitrogen may have been much higher, perhaps up here at Venus-like levels. Yes?
I thought there was a general problem with explaining how the Earth has a certain amount of nitrogen. I don't really know much about
It has.
From the chondrites explaining where the Earth got, sort of 1 bar, 0.7 of a bar.
No, that's the other way around. It's explaining why we have so little nitrogen. If you make the Earth of chondritic material, you have too much nitrogen, it has to go somewhere. So people who even hypothesize that since it's acidophile and you can form iron nitrides, there may be a lot of nitrogen in the core. Yeah. Yeah, so there's actually a lot less nitrogen in the air than there should be. Yeah. Gases, then, the greenhouse gases, this is a cartoon from Jim Casting from over 10 years ago, but basically oxygen from photosynthesis rose in the atmosphere about 2.4 billion years ago, and then to much higher levels, about 600 million years ago, ushered in the age of the animals. Carbon dioxide, with the weathering feedback and the faint young sun, should have generally decreased over time, and methane would have been high in the anoxic world before the rise of oxygen and less afterwards. That's the general idea. When you have a lot of methane in the atmosphere, if there's a methane to CO2 ratio bigger than about 1/10, you can get a Titan-like haze, except it would be more exotic chemistry because there's oxygen around from carbon dioxide and there's more nitrogen. Well, not more nitrogen around, but there's a different temperature regime, and there's also sulfur atoms, so things that don't exist on Titan. So it would be a different kind of haze. Here's the oxygen curve from various proxies in detail. Atmospheric oxygen level, less than a part per million. So imagine looking at an exoplanet that's like the early Earth. It was inhabited by microbes, but it had less than a part per million of oxygen. So you'd be looking at a reducing atmosphere. What could you see in that reducing atmosphere that would actually tell you that the planet was alive? It's a more challenging problem than looking at the modern Earth with its 20% oxygen, its ozone, and all the rest of it, which are very strong features in the reflectance spectrum. And there's this middle part of Earth history where people disagree about the oxygen levels because the proxies disagree, and there's probably 2 orders of magnitude disagreement, basically. But this period from 1.8 billion years ago to 0.8 billion years ago is called the boring billion, because there's not much evidence of climate change, no glacial deposits, not much is going on, except a few things, if you're into algae, a few lineages of algae developed. And also, it's curious, it's called the boring billion because sex appeared at that time in organisms. But oxygen's really important because we're breathing it, and it comes from organic matter, from oxygenic photosynthesis. It gets buried, separated from the oxygen, so that the oxygen can't back react with it, basically. So the net source of oxygen, curiously, is actually determined by how much organic matter you bury. And for every mole you bury, you get a mole of oxygen. And the first creatures that were pumping this out were the cyanobacteria, which some are shown here. They like to join up in filaments. The reason this is really interesting for the Earth is because it appears to correlate with biological evolution. So when we get a lot of oxygen around on the early Earth, we suddenly get things like more complicated forms of photosynthesis, like the algae instead of the bacteria. And then finally, we get the animals when we have high levels of oxygen. And it's the same old periodic table in Alpha Centauri as it is here, or some other star system. And chemistry is limited by the periodic table. And although there are 2 better oxidants than oxygen, which are fluorine and chlorine, fluorine explodes with organic matter, which seems rather unfortunate if you're going to propose an extraterrestrial biology like that. And chlorine also destroys it, which is why you use it as bleach in your bathroom. But oxygen is intermediate. It's very energetic, but it's not completely going to destroy the chemistry. So it's the best thing in the periodic table if you want to be you. And this may determine the prevalence of more advanced forms of life in our galaxy. Now there's a link to oxygen and atmospheric escape. So the last thing I want to talk about is atmospheric escape. This is a picture of the Earth in the Lyman alpha, 121 nanometers. All this red muck you see actually consists of hydrogen atoms, which are scattering the solar Lyman alpha back at us. And it shows this hydrogen halo around the Earth, which is called the geocorona. And some of these hydrogen atoms are on escape trajectories, and some of them are on ballistic trajectories coming back by gravity. Today's escape rate is very small, 3 kilograms a second. But in the anoxic Archean, with all this hydrogen in the atmosphere, much more of it gets up to the exobase, and much more of it can escape, maybe of the order of 1,000 times more escape. Now, if you go back to your 101 chemistry, if you add hydrogen to something, you chemically reduce it. If you strip hydrogen off something, you chemically oxidize it. What we're looking at here for these escaping hydrogen atoms is a little bit of oxidation of the Earth. Irreversible, because these hydrogens don't ever come back. And if it was happening at 1,000 times bigger on the early Earth, the Archean, there would have been 1,000 times the rate of oxidation. And when you add it up over time, it turns out to be quite big, the amount of oxidation. It could oxidize everything in the crust to the current oxidation state and more. So you could also oxidize part of the mantle. Well, the mantle's so big that it's effectively buffered. This is diffusion limited escape. So when we look at this, look at, say, the modern Earth or an Earth-like planet, how does the hydrogen get out? The hydrogen that we just looked at. There's a lot of hydrogen down here in the form of water vapor, but water vapor has this habit of condensing when it gets cold, like at the top of the troposphere, the tropopause. We call that a cold trap, just like in a lab apparatus for the water vapor. And up here in the stratosphere, there's only 3 parts per million of water vapor. It's really arid, extremely dry. But the methane doesn't care. That is the same in the troposphere and the lower stratosphere. And then there's upward mixing by turbulence all the way to the homopause at 100 kilometers. And by this time, the photochemistry has mostly converted the hydrogen into hydrogen molecules. And now, though, it has a problem. It has to diffuse through the thermosphere all the way to the exobase. And this is a rate-limiting step. And that's why the escape of hydrogen can't be any higher today than the rate that it takes for the hydrogen to diffuse through the thermosphere. Because once it gets to the top, it's easy for it to get out. So I've drawn this diagram as if there were 3 bottlenecks: the cold trap, the homopause, which is the beginning of the diffusion. There is potentially another bottleneck if, for some reason, up here, the situation is so cold or whatever, or the non-thermal means of escape are not operating for whatever reason, that there could be a bottleneck, probably not for hydrogen, but for certainly other species, can throttle escape. And we see visual effects of hydrogen escape. Why is Mars red? Trivial answer is iron oxides. More intelligent answer is hydrogen escape, which produced the oxygen, which oxidized the iron. And Venus, as far as we can tell, the evidence is not that great, but the near-infrared reflectance from Russian probes shows iron 3+, it's oxidized iron bearing surfaces. So Venus is probably red. It's hard to tell from the actual pictures because color balance is a real tricky problem with space probe cameras, especially ones that don't last very long because the probe dies from overheating and pressure. But the interesting thing is that hydrogen escape, so when we look back at that picture, this one, about half of these hydrogen atoms come from biology, from the methane. And the other half are from just the little trickle of water vapor that got up there. So biology is playing a role in atmospheric escape. It enhances. It takes the H in water, uses that to make organics, uses the organics to make methane, and that hydrogen then gets passed like a baton in these various forms, eventually escaping to space. And it does something else. It makes something new under the sun, quite literally. It creates a redox potential. So as the hydrogen escapes, so hydrogen in chemical reactions likes to donate its electron to some other atom that likes to hog the electron, like oxygen. And we call it an electron donor, and oxygen is an electron acceptor. And it creates a chemical redox balance, a bit like a battery. And in fact, all life on Earth operates by relaxing redox potentials. If there's a redox potential, an apple sitting on this table, and oxygen in the air, I can combine those 2 things and I can make energy. And everything else, all the microbes use some form of redox potential. But this redox potential, the one that has appeared on Earth and would appear on other planets, would be related to this hydrogen escape, at least in a generic way. Other redox potentials may not. Yeah?
Does that actually affect the non-saturated hydrogen? Or is it just, it's hydrogen that was going to escape anyways and it got used by life along the way?
It could get locked up in other materials that are not in the air. So for example, supposing life put it in organic matter and it just got buried, then it wouldn't get escaped to space. Or supposing it reacted with some substance on the surface and got in a mineral form. So it does help get it out into the air and up beyond the exobase.
Does whether it's in water or in methane, does that really make a difference?
Yes, because the water gets cold trapped and forms clouds, and so it just doesn't get to the upper atmosphere. But methane doesn't get cold trapped at a planet of 1 AU. Colin?
Yeah, I'll also add to that, there is you mentioned a trickle of hydrogen escape from stratospheric water, but one of the main sources of stratospheric water is oxidation of methane. So,
Yeah, but that's the methane vector, if you like.
so even your hydrogen from water is really hydrogen from methane.
No, there is a hydrogen from water source independently of that, which is the trickle that gets through the cold trap.
But most of the large proportion of the water in the stratosphere.
In the upper stratosphere, if you think just above the tropopause, what's the level of water vapor? It's about 3 parts per million. And the level of methane is the same as what it is. I won't say in this room because Dorian will correct me and say there's more methane in this room than in the general atmosphere. But in the general atmosphere, there's 1.8 parts per million. It's the same in the lower stratosphere. As you go up in the stratosphere, you get, I don't know, by the time you were halfway up, you got 6 parts per million of water because of the methane oxidation. Yeah. So I just want to talk then finally about the different ways to lose atmospheres. There are 3 ways. Ruth Murray Clay talked about thermal escape and mentioned non-thermal escape. Thermal escape has these 2 end members, so 2 extremes. Jeans escape, where individual molecules are escaping from the exobase, evaporating. Hydrodynamic escape, where this heating drives a pressure force and things leak out. Then there's, I prefer the word superthermal escape because these individual molecules or atoms that are escaping are sometimes called hot, just meaning that they have a high velocity. But you can also call it non-thermal. So it could be impacts of charged particles, which is sputtering, driving things out. It could be ionic reactions, like a fast charged hydrogen, H+, reacts with a slow neutral hydrogen, and it exchanges its charge, so it gives its charge to the neutral, and now it's a fast neutral, so now it can escape, and it's not bound to the magnetic field. Or the polar wind, so there's open field lines at the poles, and electrons can congregate higher up than positively charged ions, creating an electric field which can drive charged particles out to space. In fact, it's thought that helium escapes from the Earth, particularly along this path, but also hydrogen escapes along this path. And then there's photochemical reactions or ionic reactions that can generate energy and produce fast neutrals. The third way to escape is impact erosion. You're just hit by a big asteroid, and the kinetic energy that it imparts to the gases is enough to overcome the escape velocity. The Jeans escape, of course, you're talking about something in the tail of the Maxwellian distribution. So here's the escape velocity, say, and you're just talking about this small tail. And you have to integrate the tail of the distribution, particles with an upward velocity greater than v escape, and that gives you your Jeans escape. And it's a standard formalism that you'll find in textbooks. And you also find pictures like this where you plot the temperature of an exobase or a surface. So here's the Earth at 1,000 Kelvin thermosphere. And you can do this game of estimating what molecules would be able to undergo Jeans escape or whatever at this. And so you say, well, hydrogen should escape and helium should escape, although in fact helium doesn't really escape very well from this pathway, but rather from the polar wind pathway. That's because this is just dealing with Jeans escape and not the superthermal processes. So this diagram is wrong in various respects, but it's just dealing with one of the escape processes. And what you need to realize is that Jeans escape is an approximation of thermal escape, and so is hydrodynamic escape an approximation of the overall process. So in classical Jeans escape, you ignore the fact that your tail of the Maxwellian distribution is being depleted at the exobase. And so that can lead to errors, but it's not an unreasonable approximation. And then in hydrodynamic approximation, so what happens here, you have heating by XUV, you under pressure, It pushes the atmosphere out. It reaches the sound speed at the sonic level. It's still collisional, the gas. And then the gas goes beyond and supersonic and eventually reaches the escape velocity. Okay, this is hydrodynamic escape. It ignores the fact that eventually the flow has to become collisionless. At some altitude, way up here, as Ruth explained, you're going to become collisionless. So the hydrodynamic equations, which require collisions, can no longer apply. But it doesn't matter if it's actually in this regime where it goes sonic in the collisional part of the atmosphere. It's actually a pretty good approximation for the escape rate and various other things. But there are some papers, there are several, in fact, in the literature that don't do this and use hydrodynamic equations when it's collisionless. They don't have a sonic level in the collisional regime. Those papers, you should view them with great suspicion. Hydrodynamic escape is not just hydrogen escaping. The hydrogen can actually, here's the hydrogens, they can drag up heavier atoms. And so there's actually some mass fractionation. And so we can look at, say, things that should have undergone hydrodynamic escape, like when they had an early steam atmosphere, such as Earth or Venus. And we would say, well, neon, a certain isotope of neon, would be dragged off in preference to a heavier isotope of neon. And so we can compare this ratio with the solar ratio, and we find on Earth, Mars, and Venus that the ratio is less. And this may be due to hydrodynamic escape. Now, suppose we extend this idea of thermal escape to exoplanets. You can do a sort of plot like this, which Kevin Zarnley did, and we talked about a long time ago, 3 years ago in a conference abstract. And should have actually written a paper by now, but I've been too busy. What? Oh, okay. Yes. So here's a simple diagram, just plotting escape velocity and relative stellar heating. And all these nice, colorful objects are great. They have atmospheres. And these rather sad, empty objects up here are the ones which we know lack atmospheres. And you can sort of draw an empirical line that separates these two regimes. And you'll see that there's something going on, that the objects with large escape velocities and less heating are retaining their atmospheres, whereas those with a lot of heating and small escape velocities are not. And this has to extend also to exoplanets. So here's some hot, rocky, super-Earth type objects that may have lost their atmospheres. There's another way, remember, to lose your atmosphere efficiently. That was impact erosion. Let's have a look at the solar system for that. Here I've plotted the median impact velocity divided by the escape velocity. And here's our nice colorful objects. Mars has a thin atmosphere, so it's looking a bit sad. And the impact also could be asteroidal objects or long-period comets. So that's happened to have done both of those for Mars. But all of these are airless bodies. And you can see that there's a sort of division, roughly, where the impact velocity relative to the escape velocity is of order 5. And that's not, I can't justify that theoretically why it should be, but that's just an empirical observation. Now, does this matter impact erosion for exoplanets? I think it will do for small bodies. But I'm not sure how big your body has to be before it doesn't really matter so much compared to thermal escape. The thing is, there's a degeneracy. The objects that are subject to thermal escape are also going to be subject to high impact erosion. Why is that? Because they're close to their parent stars, and therefore their Keplerian orbital velocity will be big, which means that things smashing into them will have a big relative speed. So the bodies that are subject to high thermal escape are also subject to impact erosion. For example, M-star exoplanets in the habitable zone are vulnerable to both of these processes. And the smaller ones in particular will be particularly vulnerable to impact erosion. Sorry, who? Yeah. That's right. And the sort of the example that Kevin Zarnley likes to make about the solar system, we've got Titan and Ganymede, which are quite similar in size, but Titan has a 1.5 bar atmosphere, and Ganymede's basically airless, unless you're someone who's into exospheres. Well, Ganymede sits in the large gravitational potential well of Jupiter, and Titan doesn't. And so that's a reasonable explanation for those kind of bodies. So atmospheres will not exist if you're in a bad impact regime or a bad thermal regime. And small rocky planets in M-star habitable zones, I would say, are particularly vulnerable, and this is relevant for exoplanet observations, like JWST, for example. But there might be lucky ones. One could imagine perhaps something got frozen on the night side. Maybe there were slow, late, volatile, rich impactors that replenished a lost atmosphere or something like that. But things that are Mars-sized could be in the regime where what we know from the solar system would suggest impact erosion. Things that are Earth-sized, maybe not so. Somewhere between Mars and Earth, I think you maybe lose your vulnerability. And Eric mentioned the Lugar and Barnes work on pre-main sequence. That's mainly concerned with pre-main sequence luminosity of M-stars, which lasts a long time. Something we kind of ignore for the sun, but you can't ignore for M-stars. So to summarize, I talked about the origin of atmospheric volatiles, and I talked about what went on in Earth's first billion years. I talked about impact degassing of a steam atmosphere, collapse to an ocean, CO2 drawdown, stabilization by geologic feedbacks. I talked about the effect of life on Earth's atmosphere, which maybe has some relevance for exoplanet atmospheres, how basically life will extract food from the atmosphere and turn things like hydrogen into methane, how it will modulate nitrogen. It will draw it down initially as it fixes it, then it puts it back when it develops denitrification. Oxygen rose when the supply of oxygen from biology exceeded the sink of oxygen from volcanic gases and reacting with the surface. And I also speculated that hydrogen escape sets a direction. Well, I don't think this is speculation. It sets a direction to surface oxidation. The speculation was saying that it sets a direction to biological possibility by creating a particular redox potential. And I talked about the three types of atmospheric escape: the thermal, the superthermal, also called non-thermal, and impact erosion. And of those two, the ones that do the big damage are the hydrodynamic escape, which is the special case of thermal escape, right? Not the genes escape, but one end member, the other end member, and impact erosion. And then, finally, if you want more information on what I've talked about, and a shameless commercial, there's a certain book that you might want to look at, which is coming out next year, and it's fully referenced, unlike most textbooks. There's over 2,600 references. I know, because I inserted a lot of them. And this goes through principles of planetary atmospheres, the origin of and evolution of the Earth's atmospheres, and evolution of other atmospheres. So those are the three principal parts of the book, and has a really nice cover photo. That's it. Thank you. Yes?
So in your diagram, that is the with the happy worlds.
Which one? The thermal
Two of them actually.
or the impact erosion? Both of them.
Right.
Yeah.
In both cases, you're using sensitive conditions as well to estimate the criteria that you design to determine whether it should lie under the theory. So that's kind of interesting because what I would have expected is what naively perhaps is that whether it has an atmosphere or not depends more on its history than its present day conditions. So is that a statement that outgassing continues to replenish the atmosphere for a really, really long time, so that what it actually does depend on is the present day condition rather than the history?
No, I don't. Well, I wouldn't interpret those graphs quite like that. So I think it's certainly true that if you're a small body, such as an asteroid or something, you know, you're not going to hang on to an atmosphere if you're the moon, right? Even in present day conditions, because even genes escape will be enough to drive off the air. Okay, so there are some, certainly the ones on either side of that line, But the ones close to the dividing line, the atmospheric history probably matters quite a bit. And also the other thing about that plot with the thermal escape is that Kevin just did total insulation. He didn't separate out the extreme ultraviolet. And of course, the extreme ultraviolet, if that's what's important, is, has a really dramatic evolution over time, right? Where it's up to about 100 times bigger on the early sun than it is today. So I think, well, the other thing is that it's also a blunt instrument because for example, Venus, right, has lost all of its water. It doesn't have an ocean. So Venus is the way it is because of escape processes, but it has this carbon dioxide, which is not prone to these escape processes. So if you wanted to understand Venus, that doesn't really help you, except to say that it's big enough to maintain an atmosphere which is not hydrogen or has a lot of water over time. But early on, extreme ultraviolet would have done damage to Venus. But that's kind of not captured in that diagram. So it's something that needs interpretation. But the general story is true. If you're in a bad insulation regime and you have low escape velocity, you'll be vulnerable. Do you have anything to add to that, Kevin? Since you drew the plot. Oh, the impacts. Well, again, I think one which is, again, if you look at the dividing line, Mars was on the edge of that line and straddling it, depending on whether you consider the impacts from long period comets, which get hard with high velocity, versus things in the ecliptic plane, which have a lower velocity when they hit it. And it has a thin atmosphere, 6 millibars, which makes it a dead on its surface planet. So that's an example where the time history of impact erosion is responsible for that. So I think the time history really comes into its own when you consider the things close to the dividing line. But things far from the dividing line, you're right, they're stable or unstable in present conditions. Eric? Right.
Compared to, something else, compared to, say, time, we would have been, everything would have been proportionally more vulnerable, and likewise for evaporation.
Yeah.
These current properties are, plus or minus a lot of scatter, are strongly correlated with the entire history.
Yes, that's a good point. That if you're in a bad position, you're in a bad position at the beginning and later on, probably. Other questions? Yeah.
Hypothetically, so if Venus had no water and just had outgassing of CO2 without drawdown, could you get its current state today or not? Is that effectively a runaway or is it not?
So you're saying it would have had to accrete it completely dry?
It's a hypothetical.
Well, the question is, supposing Venus didn't have an ocean to start with because it accreted from material that didn't have enough water in it, could you still end up with the modern Venus the way it is without having a runaway greenhouse effect? That hypothetical, I think, was a position favored somewhat by John Lewis at University of Arizona, who used to argue for dry accretion of Venus. So I guess in the impact degassing, you could produce a lot of CO2, and since there's no water, then it would stay in the air, presumably, and not be taken up. Well, the D/H ratio, so the way John Lewis explained that was that, which is very high, right, relative to the Earth by a factor of whatever it is, 150 or something, is that you can, periodically, comets will impact just, randomly into Venus, and then if you calculate then how the D/H ratio evolves, just in recent geologic history, you can still get a big D/H ratio. And in fact, the amount of water you get in the Venusian atmosphere sort of averages out to be about right if it's resupplied by comets. So that's how he argued that one. But the reason that people didn't buy that is because the carbon and the nitrogen are there, right? So why would water be missing if it came in from the same things that made the Earth and made Mars? It just doesn't make sense that its volatile components would have been so drastically different. But we don't have direct evidence that there ever was an ocean on Venus. The D/H is not. Everybody in sort of elementary textbooks, they quote that as being evidence, but there are ways around it, as I just mentioned.
That was there at the time. That was Dave Winston's thesis.
Right.
Venus is born from.
Yes. So the paper is like Grinspoon and Lewis, 1992 Nature, or something like that. Yeah. Other questions? Yes.
Okay, I'm going to ask a somewhat crazy question.
Oops.
So let's say that we have an exoplanet that millions of years ago was terraformed, such that its atmospheric composition is completely different from what you would predict from escape processes. Could you
Right.
actually tell that?
Well, it depends what it's got in it. Supposing it's got sulfur hexafluoride or something so weird that there's no natural process that would make it, that's how you tell. There'd have to be some molecule or a chlorofluorocarbon, which is an industrial molecule. I think that's the only way you could really tell. If they're molecules that are natural, like carbon dioxide or whatever, methane or water, I don't think you'd be able to tell. Yeah. Other questions, or are we all going to go to lunch?
Let's thank David one more time.
It's very long if it had a stage of plate tectonics or some other tectonic phase. Yes? Yeah. You mean relative to Venus? Yeah, well, Venus has a surfeit of certain noble gases, which has been hypothesized to be just a sizable comet that happened to hit stochastically relative to the Earth. It's like a 1 in... So Kevin Zonnelly, who's sitting next to you, calculated that there was a 1 in 4 chance or something of the appropriate comet coming in and boosting its noble gases. But for Mars, this is a primordial isotope, and there's clearly a lot of atmospheric loss, and we can explain that from impact erosion or hydrodynamic escape. This is a diagram, a timeline, showing solar system formation after the oldest objects. So calcium aluminum inclusions, which are found in chondritic meteorites, which are dated at this time 4.568 billion years ago. So this timeline starts from then. And the Earth, the proto-Earth, would have formed during this timeline. All right, so previously I talked about atmospheric composition and chemistry, climate and radiation. and now atmospheric evolution. And again, I have a fairly solar system perspective, and I'm particularly interested in the Earth and its neighbors. So what I'm going to talk about, the origin of atmospheric volatiles and the Earth's first billion years. A volatile, in this sense, is a substance that's liable to form a gas or vapor at the prevailing temperatures. So water, carbon, nitrogen, sulfur, that kind of thing. Then I want to talk about the effect of life on Earth's atmosphere, which is relevant for exo-Earths and finding life elsewhere in the galaxy. And then we heard from Ruth Murray Clay a bit about atmospheric escape. And I'm going to talk about that more in general. It can sculpt atmospheres, it can remove them, it can change them chemically. So for example, Venus's atmosphere is the result of escape, and yet it's really thick, but it's selective escape of hydrogen and probably some oxygen that got dragged along. Atmospheres and origin of the volatiles. I'm not going to talk about the solar nebula much and accretion, but start from the basics, the beginning of having an atmosphere. So this would be 10 million years and then tens of millions of years. And during this time, it had its first atmosphere from when the impacts are coming in, vaporizing and degassing their volatiles around the proto-Earth. And then there's the moon-forming impact, which would have been followed by a similar kind of impact degassing. So this is, these are some plots. Kevin's responsible for these. And basically, it shows you impact degassing of accretion and having a steam atmosphere, which is of order tens, 100 bar. And this means that you have a blanket which blocks out infrared, thermal infrared radiation, so you're in a runaway phase, so the surface melts. And then, as the impacts decline and as things cool off, you'll have a collapse. The steam will collapse to an ocean near the Earth radius. So after the moon-forming impact, this kind of thing happened, and here's a semi-quantitative graph. So here's time in years, and first of all, we have a steam atmosphere, which, let's see, then collapses at this point into oceans. Then you're still left with a lot of carbon dioxide in the atmosphere, and this will be removed by reacting these abundances relative to solar composition from carbonaceous chondrites, which would be up here, and we can look at Mars, Venus, and Earth. And if we look at Venus, for example, we see that it's extremely depleted in water. If we look at Mars, it's depleted in all of these atmophiles. And otherwise, Venus somewhat tracks the Earth. So Mars, we can see, evidently lost air. Why was that? Probably the predominant reason was atmospheric escape, being a smaller body, but also there could be volatiles locked up as solids because it doesn't recycle them. But I talked last time whether Venus might have had an ocean for a while before going into a runaway greenhouse effect. We can get clues from noble gases. So for example, Venus has only a quarter of the argon-40, which comes from decay of potassium-40, found in the Earth's atmosphere. So bizarrely, although it has a thick atmosphere, it doesn't seem as degassed, perhaps, as the Earth is. And perhaps that's because it simply doesn't have the plate tectonic regime that the Earth does, which is continually churning stuff around and making the argon-40 come out. So if Venus did have an ocean, presumably perhaps it didn't last sphere. So volatiles mainly come from asteroid material, and that's verified by celestial dynamic models and also looking at isotopes for, say, the Earth, where we have really good information. We can look at the D2H which matches that of water in meteorites from the asteroid belt. We can look at N isotopes, which matches that also. And the dynamical models show that asteroid material is likely to have provided the majority of, say, the Earth's water, whereas comets would probably be no more than 10%. And these were acquired during terrestrial planet accretion, which can spread over as much as 10 to the 8 years. A caveat is that some primordial component might be retained inside a rocky planet from the stage of accretion where you have a magma ocean, and there's some evidence for that for the Earth. If we compare the Earth and its neighbors, then something reminiscent of Tolstoy's Happy and Unhappy Families happens, which is the volatiles are acquired in the same way, but volatile depletion on each planet is depleted in its own way. If we look at this graph, which basically is a bunch of elements, refractory ones, geochemical volatiles like carbon, zinc, and chlorine, and then atmophiles, so volatiles that like to sit in the atmosphere. And we can look at